Now that we've looked at the basic rules of covalent bonds, let's look at some of the exceptions and some of the extensions. First off, an extension to the rules. If two atoms are going to share two pairs of electrons, 4 total, they're going to form what's called a double bond. And double bonds are more stable than single bonds. Some examples are carbon dioxide, where the carbon is going to form a double bond with each oxygen, giving your 4 bonds for carbon total and each oxygen forming 2 bonds. Or CH4, where there are 2 bonds between the carbons and then each carbon is free to interact with 2 hydrogens. Triple bonds share 3 pairs of electrons, so that's 6 electrons total. So nitrogen can form 3 bonds. And a diatomic molecule for nitrogen gas is 2 nitrogens joined by 3 bonds. You also have ethine, which is your 2 carbons joined by 3 bonds, and each carbon can now bond with a single hydrogen to make their 4 bonds. Then you have coordinate bonds. This is where one atom is doing a little more of the lifting by sharing more electrons. Between carbon and oxygen, the carbon atom will share 2 electrons into a carbon-oxygen bond, and the oxygen can share 4 electrons to make a triple bond between carbon and oxygen. Well, what is this? Well, this is carbon monoxide, and that's a coordinate covalent bond. You're going to see that a lot of polyatomic ions are going to end up having these coordinate bonds. Speaking of polyatomic ions, what is one? Well, a polyatomic ion is where you have a lot of bonds in a molecule and you end up having a charge left over. So here you have ammonia, and ammonia has 1 pair of unshared electrons. Now, if you add a proton, H+, basically an H with no electrons, then you're going to get NH4+, because you have a coordinate bond between the nitrogen and that new hydrogen. And in total, there's actually a positive charge here because there is, well, a net more protons than there are electrons. You can try building this with SO3, 2-. We're going to do that on the board in class. Take some time to practice if you feel so inclined, and check the answers against Google. Now, there are, of course, exceptions to the octet rule. Sulfur and phosphorus are exceptions to the octet rule. Phosphorus can have up to 10 electrons, which forms 5 bonds, and sulfur can have up to 12 electrons, which can form 6 bonds. Now, obviously, these are exceptions, and if you're doing general chemistry, you're not going to run into these very often. This, however, is very important in chemistry, and that's bond dissociation energies. How hard is it to break a bond? A bond dissociation energy is how much energy is required to break this bond. The higher the bond dissociation energy is, that means the molecule is more stable. So here you have carbon-carbon, so your coal, basically. And that is going to have 347 kilojoules per mole. We'll get to what moles are later. And basically, that's how much energy it takes to break a carbon-carbon bond. Oxygen has a bond energy of 142 kilojoules per mole. So those are not too much compared to a carbon-oxygen double bond. That's 736 kilojoules per mole. So this means it is more energetically favorable for carbon dioxide to exist than either carbon in coal or oxygen in oxygen gas. And because you have this reaction where you give off energy to make a more stable molecule, that is why this energy is exothermic. Now, this is getting way ahead of where we are right now, but basically think if you can have a bond turn to a more stable bond, it will give off energy, and it will be energetically favorable to do so. Just like it is more energetically favorable to burn coal in air than it is to form coal and oxygen gas out of carbon dioxide. Now, resonance. Here's another interesting thing. You can draw 3 different structures for this, well, carbon trioxide. Yeah, it's kind of an odd molecule, but there are better examples later. You can make more than one of these. In each of those answers, you have 2 negative charges and you have carbon with 4 bonds. All 3 of these are correct answers, and honestly, they all kind of look the same. A resonance structure is when it's possible to draw 2 or more valid molecular structures. And you can draw both of them, and they're both equally valid. Now, why is this useful? Well, it's really useful when you get to OChem, organic chemistry in college. Also, it's kind of useful if you see one of these molecules with these double bonds on every other carbon-carbon bond, what that means is it's technically a resonance structure where you can have multiple different bonds. That means that it can actually absorb electrons more easily. So UV light can excite electrons and it can absorb electrons, and this means that this is basically something that can absorb light. And that comes in handy when we look at photosynthesis. This is beta carotene. And beta carotene is what's called an accessory pigment, meaning it can take in light and then give the energy off to chlorophyll. And most of these accessory pigments have resonance structures.